All right, guys, welcome to your study guide for our derivative review worksheet. This is just me. I'm just going to go through every problem. You're definitely not expected to sit here and watch the entire video. I would just say fast forward to the ones that you need help with. Okay, so here we go. For each problem, find the average rate of change of the function on the given interval. So the way that you find an average rate of change, I'll abbreviate it like that, is by doing y2 minus y1 over x2 minus x1. Okay, that's basically just your slope formula. These numbers here are your x values, so we'll call that one x1 and we'll call that one x2. And if you want to find your y values, then basically what you're going to do is you're going to plug in the x values that correspond to those y values. So if you want to find y2, you're going to plug 0 into this function. If you do that, you get 1. And then to find y1, we got to plug in negative 2 into this function. And that's going to give me 8 minus 4 is 4 plus 1 is 5. And so now we have our answers for y2 and y1. So it's going to be 1 minus 5 over my x2 minus x1 values. That's going to give us negative 4 over 2, which is negative 2. And that's my average rate of change. So average rate of change is just the old school Algebra 1 slope formula. Next question is asking us to find the equation of a secant line. So just to help you guys review here, if I have a function and I'm going from point A to point B, a line that goes through 2 points is known as a secant line, and the slope of that secant line is the average rate of change. Okay? But what I want to do right now is I want to find the the equation of this secant line that goes through these 2 points that are on this function here. All right? So anytime you want to find the equation of a line, we're going to use this old guy here. It's been a little bit since we've seen him, huh? Called the point slope formula. Basically, what we need is a slope and a point. Now let's find our slope. I'll call this one here x1, y1, x2, y2. So the slope is going to be y2 minus y1 over x2 minus x1. And that's going to be negative 2 over 1. So I've got a slope of negative 2 there, basically. Now I want to find my x1, which we can see up there is labeled as negative 2, and my y1, which is 4. And then basically we just need to plug those 3 things, this for m, this for x1, and this for y1, up here into this formula, and we're pretty much done. Now you could simplify this, but you can also just leave it like that. Okay. Now if you wanted to simplify it, of course this is going to become a positive, and you're going to end up with negative 2x minus 4 plus 4 is going to be 0, so that would be the final answer there, because when you distribute the 2, it becomes a negative 4 and cancels out with that positive 4. So you're just left with negative 2x. Right? So, but in a free response type of situation, I would accept this, but I would also accept this. Generally, you want to stop while you're ahead on a free response. All right. Go ahead and move on to the next one. So now we're switching gears here, and we're asking to find the instantaneous rate of change. The way that you find an instantaneous rate of change is different from an average rate of change. The instantaneous rate of change is found by taking the derivative and plugging your x value into it. Okay, so first of all, we're going to start by finding our derivative, which according to the power rule is 4x plus 1. And then we're going to plug in the x value that they're giving us, which is right here. And so that's going to be 5. And that's my instantaneous rate of change. Go ahead and move on to number 4. Number 4 is asking us to find the equation of a tangent line. So we talked about a secant line on number 2. We're talking about a tangent line now. So when you have a curve, a tangent line is a line that touches your curve at one point. And the slope of that tangent line is your instantaneous rate of change. Now, once again, anytime you want to find the equation of a line, you're going to be using, or a straight line, I should say, you're going to be using your point slope formula. So you need 3 things. You need a slope, you need an x, and you need a y. Okay, so up here they were generous enough to give us my x1 and my y1. By the way, sometimes they might just give you the x and not the y. That's a simple thing to correct, though. All you have to do is plug your x into your equation to get your y value. But here they've given it to us. My x is 1, my y is 4. Now I need to find my slope. Now, since this is an instantaneous, well, since this is a tangent line, my slope is the instantaneous rate of change, which means I need to find my derivative, which is 4x, and then I need to plug in the x value that they gave me, which is 1. So now I've got my slope, I've got my x, I've got my y. I just need to plug it all in up here. And once again, you're welcome to leave it like this if you want, or you can go the extra mile and simplify it by distributing and combining like terms. But either way, you're going to end up with y equals 4x on this particular problem. So this is acceptable, but this is as well. If it's free response, I say stop here. If it's a multiple choice, might want to go the extra mile just in case that's what they're offering as your choices. All right, let's go ahead and move on to number 5. Now the rest of the problems are just practicing all the different derivative rules that we have. Now for this one, I mean, you wouldn't have been able to get this far if you didn't already know this rule, but what the heck, we're going to talk about it anyway. This is the basic power rule. So to find the derivative of a basic power rule function is you multiply the exponent times the front, so 3 times 3 is 9, and you take 1 away from the power, and voila, we're done. All right, so you want to make sure you understand the basic power rule. Go ahead and move on to the next problem here, number 6. This is a basic power rule problem as well. However, we do need to start by rewriting it. Anytime you have a number on the top and a variable on the bottom, we're going to go ahead and rewrite that in the following way. This number, whatever's up here, is just going to stay there, but the x is going to move up next to it instead of being underneath of it, and the power is going to change into a negative. Okay. After that, you go ahead and do the derivative, which is where you multiply the 3 to the 1, which gives you negative 3, and then you take 1 away from the power. Now, technically, you can leave your answer like that, but now we're going to do the opposite of what we did when we started. What we did when we started was I took the exponent from the bottom, the x to the third power in the bottom, and moved it to the top and made it negative. Well, now I'm going to do the opposite. I'm going to leave the negative 3 right where it is, but that x to the 4 I'm going to put to the bottom and make the exponent positive. And those are just some basic exponent rules, which hopefully you guys are familiar with. So, same thing, basic power rule. I just had to rewrite it, though, at the beginning and at the end. Here's another one. This one's just included so that you guys know what to do in case you have a fraction. The rule's really the same, though. You're still going to take your power, which is 2/5, and multiply it times the front, which is negative 2/3. You're still going to subtract 1 away from the power. Now, there's a long way to do that. You could just work it out by hand like this, 2/5 minus 1. Or you can use the shortcut that I shared with you guys a while back, which is you do the top number, 2, minus the bottom number, 5. 2 minus 5 is negative 3, and you keep the bottom number as is. So it's just negative 3/5. Now, in this case, we're going to multiply straight across, so we get 4 over 15, and it will be negative because that 2/3 was negative. And then we have x to the negative 3/5. Now, this answer is fine, and I've seen my software write the answer like this, but just to show you some different ways this answer can be written, I've also seen my software write it like this, where it puts that x to the 3/5 in the bottom since it was a negative exponent. I don't think you'll see this, but it is also technically possible that it's written in the form of a radical, because anytime you have a fraction power, the denominator of that fraction power is your root, and the numerator is like a power on the variable. So, but I think that the only two you really need to be fully aware of are these two, but this is a possibility. Okay? But once again, those are just exponent rules, so hopefully they're not too surprising to you. All right, let's go ahead and take a look at number 8. Number 8, once again, this is another basic power rule problem, but it's just a little bit special because it has a radical there. But what we're going to do is we're going to change that into a 1 power right there, which means that I can rewrite this as 4 times x to the 1/4. And you can rewrite any radical in the form of an exponent that is a fraction, like so. Now we're going to do our power rule, which is you're going to multiply that 1/4 to the front number, which is 4. And you're going to subtract 1 from this power. Once again, the shortcut is top minus bottom divided by the bottom. So it's -3/4 now. The 4's cancel, and I'm left with y prime equals x to the -3/4, which once again can be written like this if you want to have a positive exponent. Or if you don't even want to have exponents anymore, you can actually rewrite it as a radical instead. Once again, I think that this and this are your most likely answers to C, but this is a possibility as well. All right, let's go ahead and take a look at number 9. More power rules, just that we're applying a property of derivatives that says that when you have a bunch of power functions being added or subtracted together, you could basically just take the derivative all the way across in the same way. So for the first one here, multiplying 5 to the front, we get -15, and taking 1 off the power, we get 4. Next one, multiplying 4 times 5, you get 20, and taking 1 off the power, you get 3. Same thing on the last one, and we're done. All right, let's go ahead and move on to number 10. All right, so at this point, now there's 2 ways you can handle this, but I'm going to tell you one way you could handle it, and then the way I want you to handle it. One way you can handle this is you can multiply this whole thing out first by FOILing, and then just do the power rule all the way across. But that's not the way I want you guys to handle it. I want you guys to treat this like a power rule. The power rules, we want to think of this and this. So that's like A and that's B. Now, anytime you want to take the derivative of 2 functions that are being multiplied together, the product rule works like this. You do A times B, but in the first set, you're going to have the A being primed. In the second set, you have the B being primed. So A prime is going to be 6x squared, and then B just stays the same. A stays the same for this one. And then here, B gets primed, which is going to be 25. I think I wrote that A wrong. Let me back up. Sorry about that. Wrote my A wrong. A is supposed to be 2x cubed minus 3. And then B prime is 25x to the 4th. And technically, could you simplify this? Yeah, but we're not going to. You can just leave it just like that. All I really care about is that you guys know how to do the power rule for derivatives. I'm not sorry, power rule, the product rule for derivatives. Beyond that, I'm not too worried about it. But if you were taking a multiple choice test and you didn't see your answer there, but you felt really confident that, okay, that's a power rule, maybe try simplifying it. All right, now this is a quotient rule. Anytime you have something over something and you want to find the derivative, you guys know this one pretty well by now. We've been doing this one a lot this year. The rule is low, d high, minus high, d low, draw a line, and square below. So the bottom's going to stay the same, it's just that it's being squared now. On the top, we do low, d high, minus high, d low. And once again, you could simplify this, but we're not going to. Just want to make sure you guys know how to do the quotient rule. Forgot my prime there. Don't forget your prime. All right. Go ahead and move on to the next one. This one's a great example of the chain rule. We have an outside function here, which is a power, and then we have an inside function here, which is just a polynomial, which is really just another power rule. A couple of them added together, actually. And the way that the chain rule works is you do the derivative of the outside. So I'm going to multiply the 2 to the front and take 1 off the power, and then whatever's on the inside stays the same. That's the derivative of the outside. Now we're going to go ahead and we're going to do the derivative of the inside multiplied by that. So the derivative of this inside piece here would be negative 10x. And for this one thing we could do to simplify would be to multiply the 2 and the 10 together to get negative 20x. And honestly, it really wouldn't be too hard to go ahead and distribute this in because it's just to the first power, so you can just distribute. But we could stop there. It's okay. Just want to make sure you guys know the product, or not the product, the chain rule. All right, let's go ahead and move on to the next one, number 13. So we've got another product rule this time. We have something times something. But this time my product rule has embedded within it a chain rule, because the first part here, the A, has an outside function and an inside function associated with it. Okay, so this one's kind of like two rules rolled into one. We're doing a product rule with a chain rule. All right, so the first thing that you would do on this is, let's start off with the product rule. This is my A and this is my B. Derivative of the A, derivative of the B. So for the first one here, the derivative of the A, we're going to apply the chain rule. So according to the chain rule, we do the derivative of the outside, which is I'm going to multiply the 4 to the front, take 1 off of the power, leave the inside the same. Then we want to multiply this by the derivative of the inside, which is just 3. So there's that. So that's the derivative of A. So we have a product rule, but one of those parts of the product rule is a chain rule. The rest of it's pretty much standard. So B just goes here. A goes here. And B prime goes here. And once again, we could really just leave it like this. We don't need to simplify it. I would say one little simplification, maybe just put the 3 and the 4 together up here to get 12, because why not? Pretty simple to do, right? But other than that, I would leave it alone. All right, let's go ahead and move on to number 14. Number 14 is another double rule situation here. First of all, you'll notice that we have an outside function. And we have an inside function, which is this entire fraction here. Now, so that means we're going to start off with the chain rule. The derivative of the outside is just a basic power rule. Finish tracing this. All right, there we go. All right, so the derivative of the outside is going to be to multiply the front by the power and take 1 off the power and leave the inside the same. But now we need to multiply it by the derivative of the inside. And the inside is going to be a quotient rule. So we have low, d high, minus high, d low. Draw a line and square below. So low, d high, minus high, d low. And we're good. All right, so we have a chain rule with a product rule embedded within it. And that's it. Once again, I'm not going to simplify this. We're leaving it just that way. All right, let's go ahead and move on to number 15. What we have here is a double chain rule, and the way that we talked about this a while back was I compared this to like an egg. You have an innermost function here. The innermost function is like the yolk of the egg. So I'm going to make this yellow. It's kind of hard to look at, sorry, but we're going to go with yellow because it's like the yolk. And then the outermost part of the egg is, you guys ever seen chickens lay those brown eggs? We're going to go with the brown shell. The outermost function is the square function here on the outside. Then we have the egg whites on the inside. There's actually a word for that. I forgot what it is, darn it. I promised myself I was going to remember it, but I don't remember what it's called, so oh well. And since I can't write with white on here, because you won't see it if I do, I'm going to write with pink, but the pink represents my egg whites. So we actually have a function inside of a function inside of a function. So the innermost function is the yolk, the outermost function is the shell, the pink stuff there is the egg whites, which surround the yolk, right? So we're just going to do the chain rule here. And the way that's going to work is we're going to do the derivative of the outermost function multiplied by the derivative of the next innermost function, which I was calling the egg whites, followed by the derivative of the yolk. And all three of those are going to be multiplied together. All right, so here we go. So as for the outer function, it's just the power function, something being squared. So that 2 goes to the front, and then the power gets subtracted by 1. Everything else on the inside is just going to stay exactly the way it is. It's not going to change. So I'll quickly just scribble that in there. Next, for the egg whites, we're going to take the derivative of the pink part, so we'll pretend this brown's not even there. And when we're taking the derivative of the pink part, the 4 is going to multiply to the front. We're going to take 1 off the power. And the derivative of the minus 3 just becomes 0, so we won't even include that. But the inside of that egg white, the yolks, that is, will stay the same here. Finally, we multiply by the derivative of the innermost function, which is the egg or the yolk itself, which is just going to be 12x squared at this point, because the derivative of that is 12x squared, and the 3 just goes away. And once again, I think you can probably expect that they're going to at least probably want you to multiply all the coefficients together. So I would put 2 times 4 times 12, which is going to be 8 times 12 is 96. And then the x to the square, just stay there. And then you have the derivative of the outermost function. It's supposed to be a 4, but I think that was a little bit more like 4. But all in all, that's kind of just extra, honestly. The real fact that I want you guys to know how to do is do the chain rule here, where you have a function inside of a function inside of a function. Okay. All right, let's move on to number 16. We're going to move into our trig derivatives. Now, most of these trig derivatives that we're going to do are going to be a chain rule. So you're going to have an outer function, which will probably be the trig function itself. And then you're going to have the inner function, which is whatever is being plugged into the trig function. And they don't put the parentheses, but I do. I like the parentheses, but they don't do that usually. All right, so the derivative of the outside. Well, the derivative of tangent is secant squared. So that's the derivative of the outside. The inside stays the same. Now we want to multiply that by the derivative of the inside, which is 15x to the fourth. And I'm actually going to put it in the front this time, just because that's usually what we do in math, is we put those constant multiples in the front like that. So that would be your derivative there, using the chain rule and the rules for trig function. So here's another trig function one. We have our outer function here, which is cosecant, and our inner function, which is 4x squared. The derivative of cosecant is, what is that? I believe it's negative cosecant blank times cotangent blank. And what goes in the blank is just what we had up there. And now we want to multiply it by the derivative of the inside. The derivative of the inside is 8x, so I'm just going to multiply that to the front and put the negative right in front of the x there, because it's negative 8. It's negative 1 times 8x, which is negative 8x. And so there's our final answer for that one. All right, cotangent. we have the outside function as the cotangent, and the inside function is the 5x squared. The derivative of cotangent is negative cosecant squared, and the inside stays the same. And then we're going to multiply that by the derivative of the inside, which is 10x. Now, typically we'll put the 10x in the front like this. But either way is technically fine. All right. Moving along, let's go ahead and take a look at number 20. Secant. What's the derivative of secant? Well, secant, the derivative of secant is secant times tangent. And what goes on the inside? This is the x squared that was originally there, but we're also going to multiply it by the derivative of the inside, which is 2x. So final answer is that. The derivative of the outside, the secant, is secant tangent. The derivative of the inside is 2x, and voila, multiply them together, you got your answer. Go ahead and take a look at number 20, another trig function. So the outside is sine, the inside is 5x to the 4th. So the derivative of the outside is cosine, and the derivative of that inside is going to be 20x cubed. Power rule. Go ahead and take a look at our last trig one, I think it is. Could be wrong, but we'll see. The derivative of cosine is negative sine. And then we're going to multiply that by the derivative of the inside, which is that x to the 5th. So the derivative of x to the 5th would be 5x to the 4th. And you could just multiply that here. Or if you want to move it to the front, you would have negative 5x to the 4th. Make that look more like 5 times sine of x to the 5th. All right, there you guys have it. All right, moving on to number 22. Moving into the arc trig functions. All right, so you have to just have these little derivative rules memorized. But the derivative of the outside function, arc cosine, is a rather odd one. It is 1 over square root of 1 minus whatever's on the inside squared. So in this, oh, and by the way, it's negative 1 on the top, my bad. So what goes on the inside is whatever was the inside to begin with. That was 2x to the 4th. That's what goes there. Next, we multiply it by the derivative of the inside, because this is a chain rule, and we end up with 8x to the 3rd. Now, if we simplify this, multiplying the 8 to the top, you're going to get negative 8x cubed on the top. And on the bottom, you're going to have 1 minus 4x to the 8. Let's do arc cotangent. The derivative of arc cotangent, once again, this is a chain rule because we do have an inside function, but the derivative of the outside, arc cotangent, is found by doing negative 1 over whatever your inside is squared plus 1. And my inside is negative 4x cubed. And we want to multiply it by the derivative of the inside, which is negative 12x squared. So multiplying top times top, we end up with a positive 12x squared. And on the bottom, we end up with 16x to the 6th plus 1. And that would be the derivative of that function. All right, now we're going to do an arc sine. Arc sine is a lot like cosine. Once again, we have a chain rule here. So the derivative of arc sine is the same thing as arc cosine that we did in earlier, but the only difference is it's not negative. So it still looks like this. We still plug in the inside here. We still multiply by the derivative of the inside. And simplifying, we do 8 times 1 on the top. And we end up with 8x over the square root of 1 minus 16x to the 4th. And we're all done with that. Number 25, the derivative of arc cosecant is negative 1 over the absolute value of the inside multiplied by the square root of the inside squared minus 1. Now my inside is 5x squared in this particular case. And we want to also multiply by the derivative of the inside, which is 10x. So let's simplify a little bit. First of all, that times that makes negative 10x. On the bottom here, you could keep the absolute value bars if you want to be safe, but just so you know, anytime the coefficient's positive and the power on your variable is even, there's no way this could ever come out negative anyway, so you could technically just get rid of the absolute value bars. But in any event, we have 25x to the fourth minus 1 on the inside there after we square it, and then we're done. Now, technically, then, this is the answer that's good enough, but you could, like I say, have not included these because we had an even power. That's important. If it's odd, you must keep those bars because depending on what you plug in, you could get a positive or negative with an odd power. But with an even power, no matter what you plug in, it's always going to be positive. So why have the bars, right? Now that we've done that, you could also technically reduce, right? Like I could take 5 and divide that into 10 to make 2. And also, we have an x on the top and an x squared on the bottom, so that could technically reduce here like this, and we could have that. All right, but ultimately, not important. What we had earlier is perfectly fine. All right, let's go ahead and move on to the next one. Arcsecant is a lot like the one we just did. It's the same, almost the same. It's just that instead of having a negative on the top, it has no negative on the top. So my outside is arcsecant, my inside is x to the fourth. So the derivative of the outside is 1 over the absolute value of the inside times the square root of the inside squared minus 1. My inside is x to the fourth times the derivative of the inside, which is 4x cubed. And then multiplying the 4x cubed times 1, we get 4x cubed on the top. And on the bottom, you can leave the absolute value bars if you want, but we don't have to since that is an even power. And then simplifying the inside, we have x to the 8th minus 1. And once again, if you wanted to, you could drop the absolute value bars since that's an even power and reduce if you wanted to afterwards. But we'll leave it like that. All right, let's go ahead and move on to an arctangent. Arctangent's a lot like arccotangent. The only difference is that when you do the derivative of arctangent, there's no negative on the top, at least initially. So the derivative of the outside there, arctangent, is 1 over the inside squared plus 1. So my inside is 4x cubed. And we're going to multiply that by the derivative of the inside, which is 12x squared. And so simplifying this, multiplying that to the top, we get this. And on the bottom, we would have 16x to the 6th plus 1. We square it. Okay, now we're moving into logs. So once again, logs are going to be a lot like chain rules once again. We have the outside function, which is the log itself. And then we have the inside function, which is the whatever we're taking the log of. So in this case, that's 2x squared. So when you're taking the derivative of a log function, you're going to do the derivative of the outside. And the derivative of the outside is the derivative of log. And the derivative of log is 1 over whatever your inside is. And in this case, that's 2x squared. And then we multiply that by the derivative of the inside. So the derivative of this is 4x. And then we can go ahead and simplify this a little bit. First of all, 4 times 1 on the top is going to give me 4x over 2x squared. And then this reduces. The 2 goes into 4 twice, leaving 1 on the bottom. And the x goes into x squared, leaving x on the bottom. And so just reducing that, we end up with 2 over x is our final answer. Exponential functions with an e, they work in the following fashion. First of all, you have the outer function, which is the e function itself. And then the inside function is its exponent, which in this case would be the 2x squared. So the derivative of the outside is just, anytime you take the derivative of e, you just get e again. It doesn't change anything. But we do need to multiply it by the derivative of the inside, which is 4x. And they would probably rewrite it so that the 4x is in the front. but technically either way is fine. All right, now this is another log function. We don't do this almost ever, and I don't really make a big deal out of these because I just don't think they're ever going to test you on it. They might, but you're technically supposed to know it, and yet I've never seen these sorts of questions asked at all. This is a log, but when you do the derivative of a log that's not an ln, it's almost the same as the other one, but it's a little bit different. So how these ones work is, so once again, it's going to be a chain rule. You have the outside function, which is the log, and then we have our inside function, which is this 3x squared here. I'm sorry, 3x cubed. Now the derivative of the log is going to be 1 over whatever the inside is, which is pretty much what it is with ln, right? But there is a little difference. We're also going to include into this ln of whatever your base is on the log, in this case 2. So we're multiplying the bottom by ln of 2 as well. Okay. Next, we multiply by the derivative of the inside, which is 9x squared. And then we can go ahead and simplify this, multiplying the 9x squared times 1 on the top. We get 9x squared over ln of 2 times 3x cubed. The 3 goes into 9 3 times. The x squared goes into the x cubed, leaving x. And so we're left with a 3 on the top, an x on the bottom, with an ln of 2 down there still. So it's the same thing as an ln. Just remember you have an ln of 2 on the bottom. That's ln of the base in this case is 2. That's the only difference, is you put an ln of whatever the base is on the bottom. So, and exponential functions other than e are very similar to the rules for e. So just like for the rules of e, you have your outside function here, which is going to be 5 to the power of something. And that power is my inside function. And so when we take the derivative of this, we do the derivative of the outside, and the derivative of the exponential is it stays exactly the same, right? Then we multiply that by the derivative of the inside, which is the derivative of 3x cubed is going to be 9x squared. But this is where it gets different than an e. With an e power or an e function, it's just this and we're done. But since we have a base of 5, we're also going to multiply it by something else, and that's the ln of that number, 5. So we have these three things being multiplied together as our derivative. A little weird, but there it is. All right. Moving on. This one's asking us to find the third derivative, which is, I wish I'd have put a different problem here. Maybe I can change it just a second. There, it's been changed. All right. It would have been kind of lame to leave it that way. Okay, so this is asking me to find the third derivative. So to find the first derivative, we just take the derivative once, which would be negative 20x to the fourth. To find the second derivative, we just do the derivative again, which is negative 80x to the third. And then to find the third derivative, we just take the derivative of that, which is negative 240x squared. That's it. So that just means you take the derivative 3 times. And same thing with any other function. I mean, sometimes it won't just be a simple power function like this. It could be other kinds, like with chain rules or product rules. Sometimes you just got to keep working your way through it till you get to the final answer. But the point is just keep taking the derivative until you get to that, whatever derivative order they're asking for. All right, let's go ahead and move on to number 33. So for each problem, use implicit differentiation. Now, we talked about this in the intro video for derivatives, just to kind of review that. So when you want to take the derivative of an implicit function is an equation where the x and the y are all mixed up inside the equation. It's not where the y is by itself like it usually is. So when you have an implicit function, we're taking the derivative with respect to x, And so, first of all, you take the derivative like normal. Like here, we have the derivative of 4 is 0, so that's just going to go away. The derivative of this is going to be 3y squared. And then the derivative of this is just going to be 5. But there is a little something different that we talked about. Anytime the variable on the bottom doesn't match the variable that you take the derivative of, like here, when we took the derivative of this, yeah, we get 3y squared, but you also get a y prime factor multiplied by it. Okay? So anytime you take the derivative of a variable that doesn't match this one down here, you get a y prime factor. The next thing you want to do is get that y prime by itself. So I'm going to divide both sides by 3y squared, and that way I can get that y prime by itself. So I'm left with 5 over 3y squared equals y prime, and we're done. So two-step process, take the derivative of everything, don't forget your y prime with the y terms, and then get the y prime by itself. Okay, go ahead and take a look at another one. More of the same, just a little bit different though. You'll notice what makes this one special is that there's two y values. Now when there's two y values, getting the y prime by itself is a little bit trickier. So here's how I've given you guys the steps in the past. The first thing you want to do is just take the derivative like we did before. The derivative of 4y is just going to be 4, but since it's a y term, we're going to put a y prime next to it. The derivative of y cubed, or negative y cubed, is negative 3y squared, but since it's a y term, not matching the bottom, we're going to put a y prime next to it. And then finally, the derivative of 3x squared is going to be 6x, and since this does match, we don't put a prime next to it. All right, now, here's where this one's a little bit different than number 33. We have two y primes. So when you have two of them, what you're going to want to do is add the y primes, well, not add, but move them to one side. So I'm going to add this 3y squared y prime to this other side here. And that way I have all the y primes on one side. Notice I didn't say the y's. I don't care about the y's. I care about the y primes. I want all the y primes on one side. Now I've got both y primes on the right side of the equal sign. The next thing you're going to do is you're going to factor out that y prime. So what that means is you're going to rewrite the entire expression. Just don't have a y prime next to them anymore, and put them in parentheses and put the y prime out here. It's like you factored out a GCF almost, right? Then what you want to do to get that y prime by itself is you divide both sides by that parenthesis set. That way these cancel, and whatever you do to one side, you do the other, right? So we have this as the final answer. Now sometimes you can go a little bit further, but here's my answer so far. Sometimes you can reduce. Now in this case you can't. The only way you could ever reduce is if all 3 or sometimes 4 terms have something in common that you can divide out, but these don't. So we're good. All right, go ahead and move on to the next one. Next one adds an extra layer of challenge to it. We're going to have a product rule right here because we have a 5x squared being multiplied by a y squared. So to find the derivative of that chunk, we're going to have to do a product rule. So here we go. The derivative of 2 is 0, so that just goes away. The derivative of 5x is 5, so that's simple. But here, we're going to have to take the derivative of that using the product rule. So I'm going to call this A. I'm going to call this B. And we're going to do AB plus AB, right? Do the prime of A on that set, and then we do the prime of B on this set. So A prime, what's the derivative of 5x squared? Well, that would be 10x, right? And then we put B as it is, which is y squared. And then we have A, which is 5x squared. And then B prime. Now, we're going to take the derivative of this, which is 2y, but don't forget, anytime you're taking the derivative of a y term with respect to x, you need to put a y prime there. So now if I were to simplify this a little bit, it would look like this. Oh, I can multiply that 2 and that 5 together actually and get 10. So I think I'll do that. Okay. Now, once again, So that's the end of it. So now I want all the y primes on one side by itself. So in this case, this whole term is going to stay here because it has a y prime, but this guy here, I'm going to move it to the other side. So now I've got 5 minus 10 one there. And now what I want to do is I want to divide both sides by this. That way I end up getting the y prime by itself. So if I divide both sides by that part I boxed, you're going to end up with something that looks like this. Now in this case, we do have a reducible situation. All three of these terms can be divided by 5. Remember, it has to be all of them, though. You can't do just one of them or two of them. You have to do all of them if they're there. So all these can be reduced by 5, which gives me the following. And this is a good answer. Now, just so you guys know, a lot of times when you're doing this, though, you could get a slightly different looking answer. It just depends on how you did step this step right here, where I moved stuff to one side. Depending on which piece you move, you could end up getting opposite signs on your fraction. So, for instance, this answer here is actually identical to this answer here. So you got to watch out for this kind of stuff. Notice that the 1 and the 1 are opposite signs. The 2xy squared and the 2xy squared are opposite signs, and the bottom ones are also opposite signs. The reason for that is because don't you guys agree that, like, for instance, let's take this fraction, 2/3. Isn't that the same thing as -2 over -3? They're the same thing, right? Because the negatives cancel. So if you change the signs on the top and the bottom, they're equal. Same thing here. This answer can be written in two different ways, and if I were you, I'd write both of them on my paper just so I remember that. And that's true for any of these fraction-y kind of problems. But it happens especially with these implicit derivative questions. All right. So now we're going to do another implicit derivative question, but this time we're going to find the derivative at a specific point, okay, where this represents the x value and this represents the y. So the first thing you want to do, of course, is to find your derivatives. So let's do that. I'm going to take the derivative of that, which is going to give me -3y squared y prime. The derivative of that is 0, and the derivative of that is going to be 15x squared. Then I want to divide both sides by the 3y squared so that the y prime is by itself. And why not reduce, right? We have 15 over 3 here, so that can be rewritten as 5x squared over y squared. And you could leave the negative on the bottom, I guess. A lot of times, though, they'll just put the negative in front of the whole fraction. Now, they want us to find the value of the derivative at this point. So I'm going to plug in 1 for x and -1 for y into this equation here. And so that's going to be 5 times 1 squared over -1 squared, which is 5 over -1, which is -5 is my final answer. All right, so that's just finding the derivative or the slope at a specific point. All right. Now, when you want to find the second derivative of an implicit function, it's a little bit tricky. There's a little bit of a twist in the middle of the problem you might not have expected. So you're going to take your function here, and you're going to find the first derivative. So that gives me 0. It gives me 2y, y prime, and that one gives me 3. Now we want to get that y prime by itself, so the first thing I would do is minus the 3 on both sides. And then I would divide both sides by the 2y. And that gives me y prime equals -3 over 2y. Now that's my first derivative. Okay. Now I want to find my second derivative, but you're going to want to remember this. That's going to come in handy in a second. So to find my second derivative, we're going to have to do a chain rule. I'm sorry, not a chain rule, product or quotient rule. I'll get it right eventually. So we do low d high minus high d low, draw a line, and square below. So my below is 2y. Low d high. Now the derivative of the top is 0. Be careful with that. It's just a constant. Low d high minus high d low. Now the derivative of 2y, that's just going to be 2. But since there's a y, we'll put a y prime there. Right? So let's simplify this a little bit first. So this goes away. Double negatives become positives. And so now I've got 6y prime over 4y squared. Heck, we could even reduce this a little bit. 3y prime over 2y squared. But we're still not okay because whenever you get this answer, they don't want you to have a y prime in the answer. They only want you to have x's and y's usually. And so instead of having a y prime in there, what we could do is we could take our answer of y prime and replace it with this. So since I have 3 times y prime over 2y squared as my second derivative so far, I can replace the y prime with this, negative 3 over 2y. Okay, so now we've got to simplify that a little bit. How do we do that? Well, just think of this 3 here as 3 over 1. Do top times top, bottom times bottom, and you end up with negative 9 over 2y over 2y squared. Next, we don't like complex fractions. We haven't done this in a while, but earlier in the year we talked about how to fix that. You're just going to multiply this fraction by the bottom number here. And that way they cancel out, which is cool. You're allowed to do that so long as you also multiply that times the bottom here as well. And so my final answer is going to be negative 9 on the top with 4y cubed on the bottom. So the little trick here with finding the second derivative of an implicit function is after you find your second derivative, you've got to replace the y prime with the equation that we got in the first step, and then you have to simplify it. Okay, that's the trick of finding the second derivative of an implicit function. All right, and then finally we have our derivative of an inverse function here. This is just a quirky little formula that unfortunately you're going to see it on the AP exam. So put it on a flashcard, make sure that you remember it and know how to work with it. So the derivative of an inverse function, I'm not writing that right. The derivative of an inverse function is given by 1 over the original function, not the derivative, prime of the inverse at whatever x value they're asking for. Okay, so that's going to be the first thing. You're going to want to set it up like that. Now the next thing that you're going to want to do is you're going to want to figure out what this is. What is f inverse of 4? Well, we're going to have to take a little side detour here for a second. So that's why I'm doing it in a different color. F inverse of 4, we need to figure out what that equals. But inverses work like this. If f inverse of 4 equals blank, that means that f of blank equals 4. Now, that's what the benefit of this little piece right here is all about. The blank is 1. So if it's 1 right here, then it must be 1 right here also. And therefore, f inverse of 4 must be 1. Now that we've got that, we're ready to move on with the rest of it. At this point, we're going to find the derivative of our function, f. We're going to plug 1 into it, and whatever answer we get, we're going to put that on the bottom down here. So this is another little detour we got to take here. Let's find the derivative of f. and plug 1 into it. So the derivative of f is f prime is equal to 20x to the 4th plus 5. And we're going to be plugging 1 into there. Which is 25. So my final detour is done. So f prime of 1 is 25. Therefore, my final answer is 1 over whatever that came out to be, which is 25. And there you got your answer. So that is how you find the derivative of an inverse function. First of all, you're going to write down your formula. The derivative of an inverse function is equal to the derivative of f at the inverse of that value. Got to do a little detour here to find that. F inverse of 4 is equal to f of 1 equals 4, so that must be 1. And then we find the derivative of the original function at 1 and plug it in. And that does it. All right, talk to you guys later. Have a good one.